Welcome, everyone, to the Victor Tyler Distinguished Lectureship in Engineering. I'm Kyle Vanderlick, the Dean of the School of Engineering and Applied Science. This is truly a wonderful moment for Yale Engineering as we today inaugurate this new lectureship made possible with a generous gift from the Honorable Guido Calabrese, the United States Circuit Judge and former Dean of our law school, and his wife, Anne. This lecture series is designed to bring to campus leaders whose contributions and insights not only reflect the broad mission of engineering, but also shed light on some of the most important technological problems of our time. The Calabreses, who inspired to create this lectureship by its namesake, Victor Tyler, a Yale graduate who received a BS in physics in 1953 and a master's in electrical engineering in 1958. For 15 years, Vic served as an electrical engineer with the national defense contractor EG&G. In the mid-60s, he was charged with identifying new business ventures for the company, one of which was the new era of electronic credit authorization systems. When E&G opted out, he left the company to found Concord Computing Corporation. It was Vic's entrepreneurial acumen which provided financial institutions nationwide with ATM processing, debit card processing, access to a national debit network, and deposit risk management. In fact, the company was the United States' largest ATM processor. Vic, his wife Mary, the Calabreses, and members of their families are here today to join us in welcoming our inaugural lecturer, someone who so perfectly embodies the spirit of this lectureship, that being Elon Musk. At age 39, Elon has already helped create some of the most widely recognized and transformative companies on the planet, including PayPal, Tesla Motors, and SpaceX. At Tesla, he is working to transition to a sustainable energy economy with all the electric Tesla Roadster and Model S sedan. And at SpaceX, he is not just preparing to send cargo to the International Space Station, but working to extend life beyond Earth. He has a bachelor's degree in physics and economics from the University of Pennsylvania, and Elon has received countless awards for his work. In 2007, he was named R&D's magazine's Inventor of the Year. He received the Aviation Week 2008 laureate for the most significant advancement worldwide in the space industry, and the American Institute of Aeronautics and Astronautics Award for the greatest contribution to the field of space transportation. The list goes on. In 2010, he received the Auto Executive of the Year Innovator Award and is the youngest recipient ever. Esquire magazine named him as one of the 75 most influential people of the 21st century in 2008, and most recently, he was named to the Time magazine 100 for 2010. It is with terrific pleasure that I welcome and present to you as our 2010 inaugural Victor Tyler Distinguished Lecturer, Elon Musk.
Very glad to be here. Thanks for having me. What I was going to talk about today was basically the importance of making life multi-planetary and kind of how I think we could get there. And I think it's one of the most significant things that will ever occur in the history of life itself. And this is really the first time in the 4 billion year history of life on Earth that it's been within the realm of possibility. First of all, I guess one should sort of look at the nature of importance itself. How do you decide that anything is important? And I think that the lens of history is a helpful guide in that the further you zoom out and the greater the span of time that you look at, the things that seem important in the moment fade away, and the things that are truly significant are still there. And if you look at the history of the evolution of life, you can say, well, what are the major elements in that history? And obviously, the advent of single-celled life, multicellular life, differentiation of plants and animals, the transition from the oceans to land, mammals, and consciousness. I think those are probably the big ones. But I think also on that list would fit life going from one planet to multiple planets. It'd be sort of at least comparable to life going from the oceans to land. And I think, given the immense difficulty of that, I think you actually need consciousness to develop in order to achieve that goal, because I can't sort of see any way that life could actually just evolve in Darwinian fashion to go across hundreds of millions of miles of irradiated space to an environment that's completely different to Earth and still live. So you really need consciousness in order to design a mechanism of making that journey, and then, I don't know if I should, actually, I'll just stand. Talking to a mic and I've got a thing on. Anyway, so it's, I think, an extremely important thing that we try to accomplish this, and it's not really from the perspective of thinking that life on Earth is in imminent danger of ending. I'm actually quite optimistic about life on Earth. I think it's likely to last for a long time. There's some chance of life being eradicated due to some natural calamity or potentially a man-made calamity. But I think most likely it will do well for a long time. Nonetheless, this is the first time that it's been possible to consider making life multi-planetary, and so I think it's wise to take advantage of that opportunity and dedicate some portion of our resources, of our collective resources, to that goal. And one can debate as to what is the magnitude, how much resources should be dedicated to it. But it's, I think not nearly as much as we dedicate to healthcare, but maybe more than we spend on lipstick. Sort of that's kind of a brackets things. And I don't have anything against cosmetics. I think they're great. But it just gives you an approximate sense of things. Maybe it's a quarter of a percentage point of the GDP, or a half a percentage point of the GDP, or something like that. In doing SpaceX, what we're trying to do at SpaceX, my rocket company, is to make some progress in that direction. And it's a very difficult goal, so I think it's going to take lots of companies and a lot of people to actually make this happen. But at SpaceX, we're going to do our best to move the ball forward as much as we can. So the way we started out was by designing a small rocket called the Falcon 1. And if that was an aircraft, it would be comparable to like a Gulfstream 5 or something like that. Basically comparable in size to a corporate jet. And it took us a couple tries to get to orbit. It's quite difficult. Getting to space is actually a lot easier than getting to orbit. So sometimes people think that SpaceX is competing with Virgin Galactic, which is being done by Richard Branson, but this is not the case. Virgin Galactic is just going to the edge of space, which requires a terminal velocity of about Mach 3. But getting to orbit requires a terminal velocity of Mach 25. And the energy scales with the square of the velocity. So getting to space is only about 2% of the energy required to get to Earth orbit. So the first launch that we did with Falcon 1 didn't even get to space. It got about 60 seconds up, and then an engine fire terminated the, well, it's a complicated story, but suffice to say, an engine fire caused the engine to stop. And then on flight 2, we actually got quite close to orbit, but had a controls issue on our second stage. It's very difficult to test the second stage in particular, because the second stage starts in vacuum at very high speed, and and high G loading. So it's really difficult to test that exactly on Earth. You can simulate it, but you can't really test it effectively. Our simulations happen to be optimistic. So we corrected that error, and then on flight 3, we changed the main engine design from an ablatively cooled main engine, which means that the chamber wall burns away slowly, to a regeneratively cooled engine, which means that you use the fuel to cool the chamber, and essentially you run the fuel through the chamber wall to cool the chamber, and so nothing burns away. But the net result was a thrust transient, an extended thrust transient that caused the failure on stage separation. But fortunately, fourth time was the charm, as it turns out. But that's how the saying goes. And on a flight 4, we made it to orbit with Falcon 1. And that was a very nervous time because we were, if we hadn't made it on flight 4, it's not clear whether whether SpaceX would still exist today. But fortunately, we did make it on flight 4, and then flight 5 was also successful, and we were awarded the contract from NASA to be the primary replacement for the space shuttle as far as cargo transport is concerned. And with recent developments this year, it looks like we will win the primary contract for astronaut transport as well. And then we launched the Falcon 9, which is a much larger version, a much larger rocket, and we launched that in June, and it looks like we learned our lessons because it actually was successful on the first flight. So I'll show you some of the videos. At some point we'll maybe release the videos of the first 3 flights. This is the music video version of the launch. It's the music we're sampling is a high roller from the Crystal Method. In the background there, you can see behind the rocket, that's the little island that we launched from. That's part of the Kwajalein Atoll in the Marshall Islands. So that was Falcon 1. Yeah, it's really difficult. The great difficulty with getting to orbit is really that velocity element. Sometimes people sort of assume that if you go up to a certain altitude, I mean, obviously you're engineers, so that you know this isn't true, but some people think that gravity kind of stops if you go up a couple hundred miles. But actually, the strength of gravity a couple hundred miles above the surface of the Earth is almost the same strength as at the surface of the Earth. It's just that in order to stay up there, you have to zip around the Earth really fast, such that the outward acceleration, the outward sort of radial acceleration is equal to the inward acceleration of gravity. And so those two null out, and that's what gives you the feeling of zero G. So here I'll show the Falcon 9. So Falcon 9 is a much larger rocket than Falcon 1. In fact, it's named Falcon 9 because it has 9 engines on the base. And each of those engines is actually operating at a higher thrust than Falcon 1. So you really have something here which is over 1 million pounds of thrust. And that's about 4 times the maximum thrust of a 747. Liftoff weight is roughly equal to a 747. This is the launch that took place in June, and it's got essentially just a structural test article about Dragon spacecraft on the top there. The launch that's coming up hopefully next month will carry an operational version of our Dragon spacecraft. And this is Cape Canaveral, so Falcon 9 launches from a launch pad we have at Cape Canaveral, whereas Falcon 1 launches from the Quad Fleet Atoll in Marshall. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off. Falcon 9. Falcon 9 is 30 hours. It's don't go transonic there. Towards the end of the first stage burn, we'll actually start shutting down engines to limit the deloading. This was the phase of flight that we were most concerned about, is the stage separation and then ignition and control after the second stage. In this case, the second stage engine was a turbo pump fed engine, which is more complex than a pressure fed engine. It was also rolling a little more than it should. The second stage roll control system was not functioning quite as well as it should have been. That was Falcon 9. Future leap to see that one get to orbit. Then I got one final video, which is worth seeing. Now this is obviously a simulation. And this is a simulation of Falcon 9 Willow Dragon spacecraft going to the space station. Basically, the Falcon 9 booster delivers Dragon to a parking orbit near the space station. Then our Dragon spacecraft maneuvers over the space station, docks, delivers cargo or astronauts, and then undocks and returns to Earth. In the simulation, the launch escape system is shown as a kind of a tractor, like that needle thing on the nose. We're actually going to do something that's never been done before, which is to build the launch escape system into the spacecraft itself, so you don't have a tractor on the nose. I think that's fundamentally safer and more efficient. Also, Dragon, once we're confident of our landing accuracy, Dragon will land on land as opposed to the water, which is shown in the simulation. So as I mentioned, next month we'll be launching the first operational version of our Dragon spacecraft. It won't dock to the space station on the first flight. It's going to just maneuver around in orbit and then re-enter, test the primary heat shield, the guidance navigation control system, all the telemetry, and then obviously the parachute recovery from the water. And then the flight after that, which is due to take place next year, will be the first flight that actually goes to the space station. So if all goes well, we'll be going to the space station and doing pretty much what you see here, except with cargo instead of people, around the middle of next year, which is shortly after the space shuttle retires. One thing that isn't apparent here is that this is actually a controlled re-entry. So this reentry, the Dragon spacecraft has a lift-over drag of about 0.25, and that's due to having an offset center of mass in the capsule. So just by rotating the capsule with the onboard engines, you can actually change that lift vector and achieve a very accurate landing location. In fact, even during the Apollo era, they were able to land with an accuracy of about 1 mile. And that was without GPS or anything. So it sort of seems like it was coming in ballistically, but actually it's a very controlled reentry. And then, as I said, this is kind of a short-term thing. Long-term, we'll land on land. So we'll just basically pop out landing legs and land somewhere probably in the Mojave Desert in California. So this is sort of where SpaceX is at this point. Now, the really big breakthrough that's needed, the fundamental invention that is needed to make life multi-planetary is a fully reusable orbit class rocket system. And this is an extremely difficult thing to achieve. The space shuttle, which is partly reusable, I say partly because the main tank is thrown away every time, and even the parts that are supposed to be reusable are so difficult to reuse or refurbish that the space shuttle costs about 4 times as much per flight as an equivalent expendable vehicle. And space shuttle is the only operating example of something that even has partial reusability. There have been many attempts to achieve, to build a reusable rocket system, but they have always been cancelled once they discovered that success was not one of the possible outcomes. But this is fundamentally something that has to be solved if life is to become multi-planetary. And it is just incredibly fundamental. If a rocket costs, say, $100 million to produce, then if you can use it once, well, then it costs $100 million per flight. But if you can use it 1,000 times, it costs $100,000 per flight. It's a pretty huge difference. And that's the reason why, for example, air flight. If you think of any mode of transport, and imagine if it were not reusable, it would see almost no use. Whether it's a bicycle, a horse, plane. I mean, just think, you'd have to have 2 horses just for a round trip. Or air flight's a good example where, 747 costs on the order of $250 to $300 million, and you need 2 of them for a round trip, and yet you can fly from New York to London for less than $1,000 if you book your ticket in advance. So the reason is because the capital cost of that 747 is allocated over, well, in the case of 747, probably 10 or 20,000 trips. So that's really the hugely fundamental thing that's needed. SpaceX, we're hoping to make some progress in that direction. Thus far, we've not recovered anything except a few little bits and pieces. But hopefully, on the upcoming flight of Falcon 9 with Dragon, if things go really well, we'll recover the first stage, and we'll also recover our Dragon spacecraft. And then, long term, we'll have to work on recovering the second stage, and then making that whole recovery process really cost effective. So that's kind of the long-term goal. I don't know if we'll be successful in that, but I think we have to try. So that's that about SpaceX. And was the main topic of my talk. But I'm happy to take any questions from people about SpaceX or Tesla or anything else.
We have plenty of time for questions, but we don't have any mics in the audience, so if you'd like to ask a question, just make sure you boom it out. So we'll start in the back, Sandro.
Two questions. One on the space part of the talk and the other on Tesla. On the space part, you just mentioned that the long-term goal is to recoverability. Currently, it's not recoverability. How do your rockets compare to see those of France and their axis in terms of performance, cost?
Sure.
And the second question is on the Tesla part. As you know, people talk all the time about range anxiety. How do you see the future of it when it comes to electric cars as far as range is concerned? What solution do you see for longer range cycles?
Right. Well, there's always Xanax, the range anxiety. Well, in terms of the cost of Falcon 9 and capability of Falcon 9, Falcon 9 is capable of about roughly 12 tons to orbit, and that's comparable to the rockets made by Lockheed and Boeing domestically, or comparable to one of the two bays in the Ariane 5. Ariane 5 is a bigger rocket, but launches 2 satellites at a time. And we're actually the most cost competitive in the world. We're about a third to a quarter of the cost of Boeing or Lockheed, and maybe half the cost of the Russians or the Chinese. I think it's just really a function of the design of the system that it's been able to be a lot more cost effective than other designs. And I'm a big believer in having engineering and production co-located, so that the iteration loop, the optimization between engineering and production can happen quickly. So I think that's often overlooked as a way of achieving cost-effective product. Whatever the design of the system sets the lowest potential cost. And if you're smart about the design, you can overcome the labor cost advantage of other countries. And then, with respect to the range anxiety thing, the way that we're addressing that with the Model S, the sedan that's coming out in a few years, is we're offering a range of up to 300 miles, an ability to charge the battery very quickly and recharge it in about 45 minutes, and then also fast pack swap, so the battery pack can be swapped out faster than you can fill a gas tank. And if you go to a range of 300 miles, you really don't need a lot of recharge stations or battery pack swap stations. In fact, you don't need any within your hometown. You maybe need them along the interstates and that kind of thing, every 150 to 200 miles. It's interesting to note that the need for recharge stations and battery pack swap stations drops with the square of the range. Because that defines the area you're able to cover. And so as the range gets bigger and bigger, the need for recharge stations drops quite a bit. And arguably, if you get up to around 500 miles of range, you don't really need any charge stations, because apart from the one at the hotel that you're staying at, because almost nobody travels more than 500 miles in a day.
Right in the middle.
So as an entrepreneur, you're working on a few moderately sized projects all at the same time, right? So how do you decide where you allocate your time and where does sleep come in?
Great question.
Well, yeah, it's definitely been a difficult thing to run SpaceX and Tesla simultaneously, and it was not really my intent to run both companies. I had hoped to just run SpaceX and then Tesla would be run by others, but when the economy had issues, and those issues particularly affected the car business. Obviously, General Motors and Chrysler went bankrupt. It was a choice of either get a lot less sleep and run Tesla as well, plus apply all my remaining capital to Tesla, or Tesla would die. And so that's, I obviously did the former. And that was definitely, it was actually definitely not fun during that period. But at this point, I feel a lot better about things, and the management teams of both companies are a lot. There's a lot more bench strength there, so I can get a reasonable amount of sleep. But for a while there, it was sort of continuous 100-hour weeks, which is, I think, that's not fun.
Thanks for your talk. I personally see you as like an amazing inspiration as an entrepreneur. And I realize there's a significant difference between being a successful entrepreneur, which you were with XCOM and PayPal, and then tackling an issue as innovative as space travel, which is actually rocket science. So I was wondering if you could speak a little bit about making the transition to SpaceX and initially putting that together.
Sure. Well, I should perhaps mention that the thing that kind of ties together SpaceX, Tesla, Solar City, which we haven't talked much about, and then PayPal and my first internet company was that in college I thought about what are the things that would most affect the future of humanity, and those things seem to be the internet, sustainable energy, both production and consumption, and then space travel, particularly making life multi-planetary. So that's the only thing that really ties them together. But going from PayPal to SpaceX was definitely a huge learning process because I'd never made anything physical before. Just basically done internet software. So there were, it was just a huge learning process. And initially I had thought that I would hire someone to be the chief designer of the rocket, but I couldn't actually find anyone who was willing to join, who was good. So the people willing to join who I thought couldn't do the job, and those who could do the job weren't willing to join. So I ended up being the chief designer of the rocket. And I think perhaps if I'd been more knowledgeable, we would have gotten to orbit sooner than Flight 4. But it was, that's kind of how it went. Yeah. So.
It seems like SpaceX makes a compelling story for privatization of space exploration. I'm curious, what do you think SpaceX and the private sector should be doing versus what NASA and the public sector should do? If there's anything NASA should be doing that you shouldn't be, and so on and so forth. What are the goals?
Well, I think NASA certainly deserves a lot of credit for the progress that SpaceX has made, in that NASA is our biggest customer. Of the launches that we've sold, about half are to NASA, about half are to other organizations. NASA has also served as an advisor on some important technical issues. So they've been very helpful, and of course, SpaceX is building upon knowledge that was created during the early days of the space program. Now that being said, NASA is still at the end of the day the government. So the government is generally not good at generally not that good at innovation and cost optimization. So it's better if NASA kind of sets the goals and says, okay, this is what we need to achieve, and then allows the private sector to figure out the right solution. I think that's been very effective with the transition away from the space shuttle to SpaceX, and then there's another company, Orbital Sciences. NASA ordered 12 of the resupply missions to SpaceX and 8 to Orbital Sciences. So I think that's a much better solution than what has been contemplated before. But we still need the NASA there to serve as a funding source, essentially kind of like a space venture capitalist, if you will, that's spending money on things that are of benefit to the whole country and arguably to humanity as a whole, but aren't necessarily of commercial value that plugs directly into the economy. It's hard to say exactly like what is the direct commercial value of sending the rovers to Mars. Or the Hubble telescope. These things are of great value to humanity, but they aren't of specific commercial value to other companies. And so that there is that important role for NASA to play in, making in funding those important objectives, and perhaps in working on, doing basic research on sort of fundamental new things that have a very long payoff period.
Peter.
You started a number of really interesting things which are fun. And I wanted to ask you, what comes first? Do you first look to whether there's a need and an economic potential, or do you look to something that you think will be interesting and fun for you to get into, and then see whether there is a possible economic potential and utility and follow? But just in terms of the innovator, what comes first with you?
Sure.
Economics or the fun?
Well, I'd say it's neither of the two. It's really kind of like a relevance optimization. It's what do I think is going to make the biggest difference to the future of humanity, and then I try to see if I can have the value of the output be greater than the cost of the input, which is necessary for any ongoing enterprise. But it's definitely not from the perspective of this is the best return on investment or anything like that. If one were to rank order return on investment and the amount of effort required, I think space and cars would be really low on the list. It is extraordinarily difficult to make an economic return on on a space endeavor, or I think on a car company. It's certainly possible, and thus far, actually, it has turned out to be a good economic return, but at great difficulty. And if I'd done, say, another internet company, the return would have been easy relative to the return that it would have yielded. So it's just from the standpoint of, am I working on things that I think will have the biggest impact on the future, and then economics. Making the economics work is necessary, just because if you don't make the economics work, then you're not going to have an impact on the future.
Right in the front, second row.
Follow up on a question. As a venture-backed entrepreneur, I'm kind of curious your thoughts on exits and whether or not, when you think of all the different companies, for example, when did you achieve success and when did you know that exit, and also why, like which of your exits or potential future exits do you see as the biggest issue?
Well, I've actually never been all that big on the exit. Both for my first company, Zip2, which basically made internet software that helped the media companies come online, and PayPal. I was the least interested in selling, but the rest of the board was, so I kind of went along with that. But I have no plans to sort of sell Tesla or SolarCity or SpaceX. In fact, I think it's very important, particularly that SpaceX not be sold, because then it would lose the philosophical goals that I have in mind.
So do you see the companies will remain private or going public in control?
Well, Tesla is public, so in theory, somebody could attempt a hostile takeover of Tesla, although it would be tricky, because I own about a third of the company, so I'd have to be doing something really stupid in order to, for somebody to do a hostile takeover. So from just doing moderately stupid things, I think they wouldn't be able to take it over. And then SpaceX, I think we'll probably take SpaceX public, but I'll even going public, I'll probably still have a majority share of SpaceX. So going public would be, give us access to low-cost capital, but I wouldn't lose control of the company. And I think with Tesla, it's possible at some point in the future, certainly not in the short to medium term, but at some point in the future, it may make sense, or shareholders may wish to sell Tesla. But I would only agree to such a sale if I felt that the fundamental good that Tesla can achieve had largely been achieved. And that fundamental good is the acceleration to sustainable transport. And that's if one looks back at Tesla and says, well, what's the best outcome I could hope for Tesla? The best outcome I could hope is that the presence of Tesla accelerated the transition to electric cars by 5 to 10 years. And the reason it's important to have that acceleration is that we have a tragedy, the commons problem in the production of CO2, where we're sort of consuming some CO2 capacity of the oceans and atmosphere, but we're not paying for that at the gas pump. And so you have to bridge that issue with innovation, and that's the fundamental goal of Tesla and Solar City. Yeah.
You women have a question. All 10 of you. Other questions? Yellow shirt, right in the middle.
Hi. So I'm curious what you would say to students because internet, energy, space, it's a lot easier for one of us to go to a website than it is to say build a wind farm or a rocket ship. But those are still hard problems. How do we try to achieve that?
Yeah, I think if somebody's just sort of starting out as kind of an engineer or entrepreneur type of role, then you need to pick something where which requires low capital. And that's why the internet tends to be a good choice. Or alternatively, if you can invent something associated with making it a more efficient form of wind energy or solar power or something like that, then I think you may be able to attract venture capital for that investment. But I think certainly space and cars would be the equivalent of like graduate entrepreneurship. Probably not wise to start out in that arena, just because the capital requirements are pretty high.
Two more questions and keep moving them out. Way in the back. Go ahead.
Hi. Thanks so much for your talk. I wonder if you might briefly touch on a few, or even just one in the interest of time, one of the major technical obstacles in creating a reusable spacecraft. And specifically, how is SpaceX going to overcome that obstacle? Is it mainly through new technology, new materials, new design methodology? Comment on that?
Yeah, so basically the fundamental issue with making an orbit class system reusable is that typically, even for an expendable system, after you've used advanced materials and advanced design techniques and that kind of thing, you maybe get 2 to 3% of your liftoff mass to orbit. So if you then start adding in recovery systems and heat shields and all sorts of things, then you're subtracting from that 2 to 3%. And then historically, when there have been many attempts to create a reusable orbital system, they found that after adding in reusability elements, they get 0 to orbit, or almost nothing to orbit. So the real challenge is improving the engine efficiency, the mass efficiency, and then just having very lightweight recovery systems, so that you can actually end up with, let's say, at least 2% of your liftoff mass coming back, at least 2% of your liftoff mass being a payload to orbit after subtracting all of the recovery systems and that kind of thing. So we do have a design in mind for Falcon 9 version 2 that in principle does achieve that. And that consists of the first stage boosting back to a propulsive landing at the launch site, and the second stage having a parafoil to a landing on either an airbag or kind of like some sort of soft landing. And in principle, that achieves the 2% of payload to orbit. So you still have roughly 10 tons to LEO capability, low Earth orbit capability. So that's what we're going to try to achieve with version 2 of Falcon 9. But it's a very tough thing, and like I said, it requires optimization across the whole system. Engines, primary structure, avionics, recovery system, the whole shooting range. There's no one silver bullet. You know, it's an overall system optimization.
One last question. Put your hands up. Now, if you're over 21, lower your hand. No, sorry. Yeah, please.
It says here that you are the Solar City is the biggest producer of solar systems, energy systems in the country. And I've been hearing a bit about what's going on in China in terms of their commitment to solar energy and the export of solar energy.
Right.
So I wonder where you think America is going to end up on this.
Right. Well, I should clarify with Solar City is the largest provider of solar power, photovoltaic solar power in the United States right now. But it's kind of like analogous to Dell computers. So Solar City does not make the solar panels itself, but it designs the overall system for a particular rooftop, does the installation, the wiring, installs the inverter, does the permitting, all that sort of stuff. So just like Dell computer doesn't make the hard drive or the CPU, that kind of thing. That actually is the majority of the cost. So if you want to install solar power on your home or business, about 40% of the cost is the panel and 60% is everything else. And so that's why it was important to have a company like Solar City to optimize all the sort of thorny bits of the what's called the balance of system of installing solar power. So Solar City will buy solar panels from a wide variety of manufacturers. But I should say that the U.S. companies are actually very strong in the panel manufacturer business. First Solar, for example, is a U.S. company. It does a phenomenal job on cost of solar power. SunPower, which is based in Silicon Valley, has the highest energy efficiency panels. So there's a huge amount of innovation taking place, and most of that innovation is driven from the U.S.
Let me take this opportunity to thank Elon Musk for an absolutely inspirational and wonderful lecture, so please join me with that. I would also like to thank the Calabreses and the Tylers for making this event possible. One of the most significant comments to me today was your answer to the question, why do you do what you do? And of course the answer was not because of the economics or because of the fun of it, because of a passion to impact the future of humanity. And I've never heard a better description of the essence of engineering than that, and that is what this lecture series is all about. So I thank you for this opportunity to have this lecture series, and I welcome everyone to a reception in the Becton student area in the Becton Faculty Lounge, right in the back of the building, for a reception with our distinguished speaker. Lastly, I'd like to offer you just a very small token of our gratitude. These are Yale cufflinks. Now, I see you're not the cufflink type. However, on the very first multi-planetary black tie event, we hope you will consider wearing them. Thank you very much.
Thank you.